Bismillahirrahmanirrahim. Assalamu alaikum. My name is Amna Farheen and I am doing MS Chemistry from the University of Management and Technology. And this article is in the supervision of Dr. Hamad Majid. So my content is about the application of diamond-based products in orbit industry. There are many applications that are of the diamond-based products in orbit industry, but we will discuss here the protective coating that is the most effective application of the diamond-based product in the orbit industry. So first of all, we have to see that which diamond-based products is used in the protective coating. So diamond-like carbon coatings that are used as the diamond-based products in the protective coatings. That is the major application of the diamond-based products in orbit industry. So first of all, we will discuss the abstract of this article. In this article, diamond-like carbon coatings are the materials that have properties similar to the diamond, such as being very hard, wear resistant, and thermally stable. These coatings are used in many industries, including aerospace, automotive, and biomedical applications. The space industry, in particular, relies heavily on the DLC coatings due to their ability to withstand harsh conditions like intense radiations, extreme temperatures, and micrometeoroids impacts. In spacecrafts, DLC coatings are used to protect components and ensure the spacecraft performs efficiently over long missions. DLC coatings are often used in the device design to detect particles in space, particularly low energy neutral atoms. These atoms, which have energies below 2 Kelvin electron volt, are present in the solar system and interstellar space. When these atoms hit a DLC coated surface, they are ionized, converted into the charged particles, and the resulting ions can be measured. This process is crucial for understanding the plasma environments around planets and the solar wind, among other space phenomena. So, if we will see the introduction of this article, so in this the introduction of this article is the the use of the DLC coatings in particular detection system, specifically the IMAP law mission, which will launch in 2025. IMAP law is designed to measure the energetic neutral atoms in space, and it is DLC coatings to convert the neutral particles into ions for detection. This method was also successfully used in the IBEX law mission, which has been operating since 2008. So indeed there are so many references which introduce the introduction of this article. So this paper compares these two missions and emphasizes how DLC coatings play a vital role in particle detection due to their high efficiency and stability. In the study, the author described the methods used to create ultra-smooth and ultra-thin DLC coatings. These coatings are less than 50 nanometer thick and have a surface roughness of less than 5 angstrom, which is important for the accuracy of the measurements. To ensure the quality of these coatings, several techniques such as atomic force microscopy (AFM) and variable angle spectroscopy, spectroscopic ellipsometry VAS are used to measure the coating's thickness and smoothness. The results shows that the DLC coated surface used in the IMAP law are highly effective at converting neutral particles into ions and have excellent long-term stability. In conclusion, DLC coatings are crucial for the space missions that aim to detect low-energy neutral atoms. They provide a durable, efficient surface for converting neutral atoms into ions, which is necessary for gathering important data about space environments. This advancement is about the coatings. These coatings are less than 50 nanometers thick and surface roughness of less than 5 angstrom. So they provide a durable, efficient, and precise surface for converting neutral atoms into ions, which is necessary for gathering important data about the space environment. The advancement in DLC coating technology are discussed in the papers and are more important for future missions and will help us better understand the cosmos. So in this figure, we will describe the DLC coatings that which play the important role in the orbit industry. So this section describes the detail of the process of creating DLC diamond-like carbon conveyance surfaces, especially for the space applications like particle detection, with a focus on handling and quality control at each stage of production. The process begins with the section and preparation of the substrate, which in case is silicon wafers. These silicon wafers are used from the Virginia Semiconductors using a method called the Czochralski technique, which is used to grow high-quality silicon crystals. The wafers have very low surface roughness, especially less than the 5 angstroms, making them extremely smooth, which is essential for the DLC coating to adhere well and perform properly. This smoothness is confined through atomic force microscopy AFM tests. To create the required shape for the project, the wafers are cut into the specific sections called facets. This cutting process must be done carefully to avoid the damaging the polished surfaces. The cutting procedure known as the desizing must prevent the polished surfaces from the getting scratched or contaminated. If the surfaces isn't protected, it can become damaged, which would affect the final product's quality. The wafers are also cut into the smaller square test samples that will be used for testing the conveyance efficiency. Before applying the DLC coating, the silicone wafers must be cleaned to remove any contamination. Before applying the DLC coatings, the silicone wafers must be cleaned to remove any contamination left from the desizing process, as even small particles can compromise the quality of the coatings. The cleaning process is done in a clean room ISO 6 level, which is very clean environment, using two methods, wet cleaning and dry cleaning. In wet cleaning, the wafers are first cleaned with high purity isopropyl alcohol and deionized water, both of which are very effective at removing contaminants. The deionized water used has a very high resistivity, greater than 115 MeV, making it ideal for cleaning. The wafers are repeatedly rinsed in deionized water and IPA to ensure thorough cleaning. Nitrogen is then used to dry the surface after rinsing. After wet cleaning, dry cleaning is performed using UV ozone cleaning. UV is ultraviolet ozone cleaning. This method involves using UV light to generate ozone, which reacts with any other organic material on the surface of the wafers. This cleaning process helps improve the adhesion of the DLC coating. The wafers are placed under the UV lamp, which produce ozone that reacts with the organic contaminants, breaking them down and removing them. This method is effective because it doesn't damage the surface of the wafers, and it's particularly useful for ensuring that the surface is pristine before the DLC coating is applied. The wafers are checked under a microscope to ensure they are clean. If contamination is further cleaning steps is found, further cleaning steps such as additional rinsing or wiping with acetone are carried out. This is critical because any contaminants could interfere with the coating process. Once the wafers are thoroughly cleaned, they are ready for the DLC coating or diamond-like carbon is a hard, smooth material with properties similar to the diamond. This coating is deposited onto the polished wafers using a method called plasma immersion ion deposition. In this process, a plasma is generated to allow carbon ions to bond with the surface of the silicon wafer, forming a thin DLC film. The thickness and quality of this film are crucial for the performance of the conversion surfaces, so careful control of the deposition process is necessary. After the coating is applied, the surface quality is measured to ensure the coating meets the required specifications. This includes checking the film thickness, surface roughness, and charge conversion efficiency. How well the surface can convert particles into a measurable signals. During the DLC coating process, it is essential to maintain the cleanliness of the surface. Any contaminant, especially large particles on the surface, can distort the coating and affect its properties. Special care is taken to clean the surface if any contamination is noticed after the coating. The wafers are checked under a microscope to ensure they are clean. If contamination is found, further cleaning steps such as the additional rinsing or wiping acetone are carried out. This is critical because any contaminants could interfere with the coating process. Once the wafers are thoroughly cleaned, they are ready for the DLC coating. DLC or the diamond-like carbon is a hard, smooth material with properties similar to the diamond. Properties. Special care is taken to clean the surface if any contamination is noticed after the coating process. If necessary, the coated surfaces are cleaned with the deionized water and IPA to remove any particles that might have settled on the surface. For example, an AFM image is used to compare the surface roughness of the coated surface before cleaning. After cleaning, if large particles are present, the surface roughness can increase significantly as shown in the image, where the roughness increased from the 0.47 nanometer to 2.68 nanometer due to the contamination. After cleaning, the roughness returns to 0.35 nanometer, demonstrating the effectiveness of the cleaning process. Once the DLC coating is applied on the surfaces are cleaned, they must be carefully protected. The DLC surface is sensitive to UV light, which can degrade its performance over time. UV exposure can cause a hydrocarbonaceous layer to form on the surface, reducing efficiency of the conversion surface. Therefore, after the DLC coatings, the conversion surfaces are kept in the light blocking containers to protect them from UV exposure. These containers are carefully designed to avoid touching the polished surface and to minimize movement during transport, which could cause scratches. The coated surfaces and substrates must be stored and transported in containers that provide scratches. So in this figure you can see the DLC coated surface and the substrate. So in the substrate preparation, the coated surfaces and the substrate must be stored and transported in containers that provide several protections. They must protect the highly polished surfaces from the scratches, minimize the risk of contaminants entering the storage or transport area, and shield the conversion surface from the UV light. Initially, containers like gel pack, which are frequently used in the semiconductor industry, were considered but discarded because they couldn't be refused and could trap dust and contaminants. Other options like aluminum cassettes and polypropylene coin containers were also considered but had limitations in terms of handling, ease, and protection. Finally, aluminum trays were selected for the short distance transport as they offered an easy way to load and unload the sample while keeping them protected. However, the trays needed to be carefully cleaned to avoid contamination as some trays like those made from the item had detergent residues that caused contamination. The final choice was aluminium trays with electroless nickel flashing, which were thoroughly cleaned and used for storing and transporting the substrate and coated conveyance surfaces. To prevent contamination during handling, vacuum vents are used to pick up the substrates, avoiding direct contact with the hands or gloves. So in this picture you can see that how we can cover or we can save the substrates or the DLC coatings. And in this section we have to see that the storage and the transportation of the DLC coatings on the substrate and the material or the other material. So in this technique, the AFM, atomic force microscopy, what is the atomic force microscopy? Atomic force microscopy is highly resolution imaging method used to examine the surface structure of the materials at the nanoscale. It works by scaling a sharp probe tip over the surface of a sample. The probe interacts with the surface through atomic surface forces, and these interactions are measured through laser deflection techniques. This allows for creating highly detailed topographical maps of these surfaces. For roughness measurements, RQ means root mean square roughness is used because it is more sensitive to outliers like contaminants particles than RA. RA means average roughness. The study uses AFM to measure surface roughness, especially after cleaning or coating. With high precision, the probe tip and scanning mode peak force step trapping was specifically chosen to reduce the sample damage and enhance accuracy. So this is all about the AFM, means atomic force spectroscopy or microscopy. So if we will see the choose that is the coating. So in this coating, DLC diamond like carbon coatings are applied to surfaces using a method called PIID. PIID means plasma induced ion deposition, or a variant of PECVD, plasma enhanced chemical vapor deposition. These coatings are applied to enhance the surface properties, which are very important to enhance the surface's properties. This deposition is done in a vacuum chamber using gas molecules where the desired material remains after breaking down the gases. So in this section we can use the gas molecules or gas for the breaking down of the material. The coating are applied to enhance the properties of the surface. The deposition is done in a vacuum chamber using gas molecules, and in this figure you can see the whole structure where the desired material remains after breaking down the gases. The coating process involves multiple steps: argon plasma cleaning or prepare the surface, DLC film deposition, and hydrogen termination to reduce surface reactivity. These steps aim to create a thin DLC film with a consistent thickness about 45 nanometer. That thickness is the about 45 nanometer, and low surface roughness, has less than 5 angstrom. So this is all about the coating that are the DLC coating, means diamond like carbon coatings. So if we see the F section was base means variable angle spectroscopic ellipsometry. WACE is a technique used to measure the thickness of thin films like the DLC coating. A polarized laser beam is reflected off the film, and the change in polarization is analyzed to determine material properties including film thickness. This method is non-destructive and can measure films on the nanoscale. The process involves measuring light reflection at different angles, and the results are analyzed using a software programs that can compare the data to know models of the material. In this case, WACE measurements indicated that the DLC film thickness ranged from 35 to 55 nanometer. which was consistent with other measurement techniques like scanning electron microscopy, that is the SEM. And we know that in the SEM we can use the different electron beams and that can be shoot from the electron guns, and these electron guns are located at the top of the device's position, that are there from where the electron beam can be directed on the sample or the surface of the sample, and from this electron beam we can scan the area or the surface of the sample that is the under examination. So if we will see the section D, conversion efficiency measurements. So what is in the conversion efficiency measurements? So in this section, the conversion efficiency of surfaces is crucial for detecting particles in space. Especially for ion detection, the performance is determined by how well the surfaces can convert neutral atoms into the ion. The conversion efficiency of the surfaces is crucial for detecting particles in the space or in the orbit industry, especially for the ion detection. The performance is determined by how well the surface can convert the neutral atoms into the ion. The step up involves using an ion beam directed on this at the surface, where it interacts with the surface, causing the emission of the secondary electrons and ions. And these secondary electrons or ions are also produced in the SEM. These are then measured by a detector. The goal is to have a narrow angular distribution or reflected particles, which lead to the better ion detection efficiency. The negative ion yield is calculated as the ratio of negative ions to total scattered particles, means both neutral atoms and negative ions. The conversion efficiency of the DLC surface for hydrogen and oxygen ions is measured, and the results help understand how well the surface perform in the space-related applications. So we will see the conclusions of these techniques. These techniques together follow the precise characterization of the space properties such as roughness, film thickness, and ion conversion efficiency. The study aims to improve surface coatings. So this is all about the coating conversion efficiency measurements. So the number of the neutral atoms and the negative ions scattered of the conversion surface sample is used to calculate the negative ion yield, where the number of the registered atoms and ions that depends on the detection efficiency and the number of the registered counter informations. And from this article you can see the explanation of these wires or designs. The 2D MCP detector measures the angular distribution of the reflected beam. The extent of the 50% contour line is the angular distribution is read to out to the registrator full with the half maximum in the azimuthal or the polar directions at different incident energies. The negative ion yield for hydrogen and oxygen at a few energies ranging from 200 to 1000 electron volt per atom has to be calculated for the IMAP load DLC conversion surface. The same experiment has also been performed with the noble gas neon and helium to crack for and subtract the negative ion contributions. For particles sputtering off the conversion surface, neutral noble gas atoms cannot be directed using the charge conversion techniques because the noble gases do not create the stable negative ions. Their sputtering of the surface atoms, the Sockland sputter contributions, is on the indirect way to detect them. For hydrogen at energy 600 electron volt and oxygen below 400 electron volt molecule ions H2 positive and O2 positive at twice the nominal energies have been used at the source beam. So in this we have discussed the conclusions and effects. So now we will discuss the results and discussions. So what is about the results and discussion of these articles, and the results and discussions. In this section we will discuss the results from various tests conducting on the DLC diamond like carbon conversion surfaces that were created from the IMAPLO missions. These surfaces are designed for the neutral atoms conversion in space instruments, specifically for the detection of the particles in space like hydrogen, oxygen, helium, and neon. So, time and money are saved by using the witnesses facts of for the quality measurements, but more significantly, this is avoided unlimited contaminant of the final conversion surfaces that were supposed to be installed on the flight IMAP or unit such as could have occurred from the transport between facilities and non-clear room operation. DLC film has been applied to 10 sets of flight mode FM convergence surfaces. The coating procedure produced 70 possible flight facts. 10 witnesses faced store on a monitor on the thickness and the surface roughness of the DLC film, and the 10 square test sample to gauge the conversion efficiency, thickness, and the surface roughness of the DLC film. Since the ILENA setup has restriction on the sample size that can be mounted within a test chamber, the conversion efficiency measurements were only conducting on the square test sample, the DLC film thickness of 100 nanometer, as was the cause of the IBEXL conversion surfaces had surface roughness more than 10 angstrom accurate according to the result of the initial coating attempts. The angular breadth of the reflected beam was negatively impacted by the surface roughness, which made it wider and decreased the conversion efficiency of the conversion surfaces and consequently the instrument detection efficiency, or for example the geometry factor. A more collimated beam of the converted ions is typically produced by a refracted beam with a narrow angular dispersion in the polar and azimuthal directions. This enables the guiding magnets to collect the beam towards the post-acceleration subsystem more efficiently. The angular distribution of the reflected beam narrow as a result of the surface roughness being reduced due to the DLC layer thickness reduction. According to the preliminary findings, the 40 nanometer DLC layer replicate the conversion effectiveness of the IBEXL convergence surfaces by providing surface roughness. TLC convergence surfaces demonstrated convergence efficiency comparable to IBEXL low convergence surfaces as a result of additional production process improvements such as meticulous substrate cleaning the prior to coating and contamination control during the coating and diagnostic purposes. So if we see the key factors of the quality measurement, the IML or TLC conversion surfaces were tested for surface growth, surface roughness, conversion efficiency, and film thickness and uniformity. These measurements were taken at different locations and times after the DLC coating was applied. And in this figure, we can see all these results, all these instructions that we have said that data corrected for the sputter contribution or the negative ion yield for the streaking hydrogen and oxygen beam. For helium and nitrogen, the displayed line theta n is not the directed charge conversion efficiency but rather than the sputter yield of the negative ions. Some measurements were taken at the Southwest Research Unit Institute's SWRI, while others were performed at the University of the Bournemouth later. To avoid contaminating during transitions with the witnesses' spaces, reference samples were used for quality checks rather than the actual flight samples. This helped keep the final flight. To avoid the contamination during the transport, the witness facets Reference samples were used for the quality checks rather than the actual flight sample. This helped keep the final flight sample clean and uncontaminated. The test samples were categorized into the final model FM, conveyance surfaces, witness facts used for monitoring, and square test samples used for measuring the conveyor efficiency, thickness, and roughness. Coating process. The DLC coating process was applied to 10 sets of the flight model FM conveyance surfaces, resulting into the 70 flight facets, 10 witness facets, and 10 square test samples. The DLC film was applied with an initial target thickness of 100 nanometer, but the result of these early attempts showed that surface roughness above 10 angstrom caused a wider angular dispersion in the reflected beam, reducing the conversion efficiency. The rougher surfaces led to the poor ion conversion because the reflection was less collimated, meaning the beam was scattering more, making it harder for the guiding magnets to focus the ion efficiently. This affects the overall performance of the instruments. So to improve this, the thickness of the DLC film was reduced to around 40 nanometer, resulting in a much smoother surfaces and better conversion efficiency, similar to the results seen with the IBEX and low convergence surfaces. If we will see the optimization, so the DLC layer was optimized to a thickness of 46.7 nanometer with a surface roughness of 3.4 angstrom, resulting in more reproducible and consistent conversion surfaces. The improvements were made possible by refining the coating process, including cleaning the substrate carefully and maintaining a clean environment during the deposition and testing. The ILENA ion beam facility measurements for the conversion efficiency was performed using square test samples. These samples were exposed to ion beam of hydrogen, oxygen, helium, and neon, and their negative ion yield and angular scatter distribution were measured. The test shows that the DLC coated conversion surfaces were able to achieve consistent conversion efficiencies and angular scatter distribution across different samples. So the results from the ILENA facility, which we have achieved or received negative ion yield, was measured for the hydrogen, oxygen, and helium and neon beam with the energies ranging from 195 electron volt to the 1000 electron volt. The yield was consistent across the field flight model and the engineering model samples. Angular scatter was measured in both the polar and azimuthal directions, showing that the reflected ion beam had consistent dispersion characteristics. Minor variations in scatter width was considered experimental artifacts due to the precision limitation of the setup, not due to the actual difference in the sample quality. Sputter yield, the amount of the negative ions produced through sputtering, was measured for helium and neon ion. The sputter contribution were relatively low, ranging from 1.5% to 5% for different ion species. Conversion efficiency, consistency, despite differences in film thickness and surface roughness, the negative ion yield and angular scatter for the IMAP low DLC conversion surfaces were obtained. And conclusions or results overall, the IMLO DLC conversion surfaces demonstrated the reproducible performance with the consistent convergence efficiency and angular scatter characteristics. The improvements in film thickness and surface smoothness were essential in achieving the outcomes. So now we will see here the summary of this article. The summary is that in this summary, the key points are about the DLC conversion surfaces and their preparation, coatings, and testing for use in the IMAP information mission. So DLC conveyance surfaces for the space use. The DLC coated conveyance surfaces are designed for detecting neutral atom with energies between 10 electron volt and 2 electron volt in space instruments. These surfaces are an important part of the IMAP mission payload coating and substrate preparation. The substrate used for the conveyance surfaces are carefully prepared and cleaned to ensure the DLC film adhere well and provide the desired performance. The coating procedure was non-invasive, allowing the diagnostic measurements without damaging the surfaces. Ultra thin and ultra smooth coatings. The DLC coatings has a thickness of 46 nanometer and a surface roughness of the 3.4 angstrom, which is the ultra smooth. This smoothness is essential for the surfaces to function properly in space instruments where smoothness and uniformity play a crucial role in an ion conveyance efficiency. Importance of cleaning and contamination control. The key to achieving smooth conveyance surfaces lies in the careful cleaning of the substrate before deposition and contamination control throughout the coating process. Use of WAVES and AFM. Use WAVES variable angle spectroscopic ellipsometry was used to measure the thickness and uniformity of the DLC coating, while AFM atomic force microscopy was used to measure the surface roughness. These tools were crucial for monitoring the quality of the conveyance surfaces during production. Automated production process. In this section, to further improve the efficiency of the production process, the authors recommended fully automating the process. This would minimize handling the sample, reduce contamination risk, and improve overall production efficiency. Importance of the IMAP mission. The DLC convergence services are crucial for the surface of the IMAP mission, which will study space phenomena at the L1 language point between Earth and the Sun. The surface will be the part of the instrument that measures in neutral atoms in space, helping scientists understand space weather and its effects. So this is all about this article. I hope you will understand everything in this article. Thank you so much.